back to Chemistry 3120. Today's lecture 13, and today we're going to start chapter 26. This chapter is focused on the Aldol reaction, and it's going to be broken up into several different parts. So the first part will be looking at the aldol reaction itself. Then we'll look at something called cross condensations. And then we'll look at how we could make specific enol equivalents from what we learned in chapter 25 and apply that to the aldol reaction. We will look at intramolecular aldol reactions, and specifically we'll compare and contrast thermodynamic versus kinetic formation. We'll spend some time on enones. And then lastly, we'll look at the stereochemistry of the aldol reaction. So there's quite a bit of material, and as I mentioned, this is in chapter 26 of your textbook. And so I'm not going to put this all in a single YouTube video. Today this will be lecture 13. And then we'll probably do one of these ones as an individual lecture. So 14, 15, 16, 17, 18. So we're looking at around chapters 14 to 18 for this entire chapter. All right, so let's get started. All right, so the aldol reaction is actually a really great way to make carbon-carbon bonds. And its name comes from the condensation of an aldehyde to generate an alcohol. That's why it's called aldol, because the final product contains both those functional groups. So let's first look at the base-catalyzed mechanism of an aldol reaction. And for now, let's look at self-condensation. So we're just dealing with a single molecule. So this is acetaldehyde. And in order for us to go through the aldol reaction, we need to form a nucleophilic enolate. So we'll take some kind of base. The base will remove this acidic proton to form an enolate. And then this enolate, as you know, is nucleophilic. And then it can condense with another molecule of itself. And as you've learned already, many times already in this course, aldehydes are very electrophilic. So the enolate will come and react with the aldehyde, as I'm showing you here. And then what's going to happen is this will pick up typically we might do this in a solution of something like water or hydroxide. So this will pick up a proton from the conjugate acid of the base that initially picked up that proton. And now you're left with this compound here, which is your aldol product. So this is what we call base-catalyzed aldol reaction. And you can also do this reaction under acidic conditions. So let's compare and contrast what that might look like. Okay, so the acid catalyzed aldol reaction, and let's look at exactly the same substrate molecule. So what you're going to do is you're not going to have base present, or at least a strong enough base to remove that acidic proton, but you're going to have an abundance of protons. So in this case here, let's use a general Bronsted acid, and this is going to come, and the electrons from the carbonyl will come pick up a proton to make this molecule a highly electrophilic form, activated form. And then what you're going to do is you're going to have some very weak base, Let's call this actually B for base. This will come and this will form not an enolate, but an enol. And an enol is very similar to an enolate. They're both nucleophilic. However, enolates are much more nucleophilic because you have a negative charge, whereas an enol is neutral and is weakly nucleophilic. So because it's weakly nucleophilic, when it reacts and condenses, it can't condense with just the aldehyde. It needs to use the activated aldehyde through protonation that we already identified and made over here. So we will take this protonated aldehyde, and now your enol can come, electrons come down, the double bond comes and attacks the aldehyde like I'm showing you here. And what you will generate is this molecule here. Now, because the enol came down and attacked, this oxygen is now positively charged. You have this oxonium ion, so you now need to remove that proton in order to go to the neutral species. So this is where you can have a base or the conjugate base of what was protonated earlier to pick up that proton. And there's your product. So it's the same product, whether you do base or acid catalyzed chemistry. So let's just summarize here. Great way to make carbon-carbon bonds. And carbon-carbon bonds are extremely important in organic chemistry because this serves as a backbone and framework to make more sophisticated types of structures. So you can imagine that this reaction is quite versatile because we're using a very simple aldehyde, but you could imagine that if we use different aldehydes, different combinations, this could give us access to a wide variety of products. Now both these reactions here, this is an aldol product, however they are prone to dehydration. So if you actually take, well they're both the same compound here. If you take these compounds and if you dehydrate them, typically you need some heat and you need some base or acid to promote this. But what happens is that you lose this proton here and you lose water and you end up forming a dehydrated aldol, which would look like this. So aldol products can also dehydrate. And the mechanism by which they dehydrate depends on whether you are in acidic or basic condition. So let's take a look at both of them. Mechanism for aldol dehydration. And like we've done before, why don't we start with the base catalyzed first. Okay, so there's your product there, your aldol product. We're going to dehydrate it. So remember, we have a lot of base present. And your base is going to come, and you know that you need OH to leave. Now water, or OH, if it leaves as OH minus, that's not the best leaving group. And let's think about what we know about acid-base chemistry. You know this proton here has a pK of around 20, and the reason it has a pK of 20 is because the carbanion that's formed here actually is resonance stabilized through this carbonyl to form an enolate. So for base catalyzed dehydration, what we're going to do is we're going to draw the conjugate base of this reaction. So remember, this is simply acid-base chemistry. That's your base. You can think of this here being your acid, and therefore this is the conjugate base. Once this is delocalized appropriately, the way I like to think about this is that this now has electronic energy, and now it can flow through, kind of like a roller coaster, through these bonds appropriately, and then that gives it enough energy to kick off the hydroxyl group. So this is an elimination reaction. However, it's not an E2 mechanism, it's an E1 mechanism, and it goes through the conjugate base. So this is also known as E1CB mechanism. Elimination through the conjugate base. In contrast, let's look at acid-catalyzed dehydration. So again, starting with the same aldol product, this OH needs to leave, and we got to pick up that proton. But under acidic conditions, OH minus can never leave. Okay, so please remember that. Depending on the conditions that you have, you cannot have OH leave. Acid catalyzed, right? You can't have OH minus. Similar up to base catalyzed, you cannot protonate here because you don't have protons present to protonate this to make it OH2, to make it water. All right, so always be aware of the conditions that you're under. So under acid catalyzed conditions, as we've already discovered, you have a lot of acid present. So in order to make this OH a good leaving group, you're going to protonate it. OH2 or H2O is a good leaving group. You can see here that it's happy to leave because you have an oxonium ion positively charged. And then a base can come and remove that. Okay, a very weak base because this is such a good leaving group. Okay, so typically what we can do is we could have the HA, and you could even think of HA as being something like, you know, H3O plus perhaps, and then that would leave you with something like water as your conjugate base. Water or the conjugate base would now come, eliminate, and you will now generate your dehydrated product. Depending on what you have substituted here, you could undergo this via E1 or E2. The one I've shown you here is E2. However, you could imagine if you have a fully substituted carbon, even perhaps resonance stabilized, you could get departure of that leaving group first, followed then by elimination. So E1 or E2 mechanism. These reactions typically require heat It's an entropically favored process, but you got to heat it up in order to get removal of that water. It's often difficult to predict whether you'll get the dehydrated product or you'll get the initial aldol product undehydrated. So sometimes in some of the problems that you'll look at, maybe there'll be a clue in terms of us giving you a molecular formula, or we might tell you it's dehydrated or not. This will become more clear as we go through some problems. All right, so those are the basics of the aldol reaction, and you certainly have seen some of this from second year organic chemistry, I'm sure. So let's go through the aldol reaction of an unsymmetrical ketone. Okay, the aldol reaction that we'll look at, or the molecule that we'll look at, will look like this. And let's pretend we have some kind of phase transfer catalyst, but the important thing is that we have hydroxide, which is our base. So let's look at how this molecule will come and condense via the aldol reaction. So, hydroxide will remove the proton. You will form the enolate. Right, and then the enolate can react with another molecule of itself. So the electrons come back down, electrons go through the carbon, attack that ketone as I'm showing you. This is the new carbon-carbon bond that we've made. Electrons go up. And that's our compound here. This now can pick up a proton from the conjugate acid of hydroxide, which would be water. And this would be your aldol product. Okay, so pretty straightforward, very similar to what we had seen with the aldehydes, right? The only difference is that it's a bulkier molecule and it's ketones, but the same principles apply, self-condensation. If this were to dehydrate, you have an acidic proton here, right? Your base would come, form the conjugate base, like we just shown right behind here, and then those will come down and remove the water. So if you did dehydrate this, or if you were asked for the dehydrated product, that will look like this. Okay, so you now have removal of the water, H2O, double bond here, and you have this fully substituted molecule. Okay, one question that typically comes up, and one of the challenges of doing this virtually or in pre-recorded lectures is that you're not here with me, but one of the questions that comes up almost every year by students, it's a great question, and the question is, well, why doesn't OH attack the ketone, or the aldehyde in that case? Right? Why is it only picking up the proton? Well, the answer to that is it can absolutely react and act as a nucleophile to this carbonyl here. And maybe let's take a look at what that looks like. Okay, we know what the final product is. Let's use black. It's a lot clearer, I think. Right, so why doesn't OH react here? And if it does, you would generate this compound, right? And certainly that makes a lot of sense, right? Why doesn't this happen? Well, it actually does happen. It actually does happen. But the problem is, or the thing is, that this compound here looks like a tetrahedral intermediate. So these electrons are going to want to come back down. And then what you're going to do is you're just going to kick back off that hydroxyl group. So this process here is entirely reversible, and it's non-productive, meaning that there's no outcome or productive outcome of this. So that just goes back, hydroxide gets back and released, and then that hydroxide can try again. If it decides to act again as a nucleophile, just goes here, terminal step, goes back. Once in a while, it'll pick up that proton, form that enolate, and then that enolate can come and form that carbon-carbon bond. Okay, so the last reaction before we move on to the next lecture is looking at the Aldol reaction of not just aldehydes and ketones, but we're going to look at unsymmetrical esters. Okay, so let's take a look at an ester that looks like this. Specifically, let's look at this lactone. A lactone is simply the name for an intramolecular ester. Let's think about what kind of base we'd like to use. Should we use something like a hydroxide base? Now this is where I'm glad we had that discussion about hydroxide acting as a nucleophile, because as you recall, it's reversible. But if you do actually add hydroxide as a base here, indeed you'll get reaction occurring here, electrons will go up, but then the problem is when they come back down, you can now break this carbon-oxygen bond and open up that ring. So in this case, you have to be aware of hydroxide acting as a nucleophile, and it can destroy the product, or your starting material. So we have to use now a non-nucleophilic base, and we want a base that will pick up these protons here. So a good base that comes to mind, a non-nucleophilic base, we can use something that we learned last chapter called LDA, right? Lithium diisopropyl amide. This was a good, strong, sterically hindered base. You can think of this again like N-. And what this will do is this will pick up the proton and form the enolate. Once this enolate's formed, this can come and react with another molecule of itself. Electrons come down. The enolate can now react. Right there, electrons go up. And you form this compound here. Okay, so there's nothing new about, the mechanism. And then this O- can pick up a proton from the conjugate acid to generate this. As I'm showing you here. Right, so understand that this, from here to here, is your new carbon-carbon bond, right here. then here we pick up the proton, and that would be your aldol product. If we do dehydrate it, then you're going to pick up this acidic proton adjacent to the carbonyl, the alpha proton. You're going to form the double bond here, and water will be gone. So the dehydrated product, if this is heated up, would look like so it'll be a 1, 2, 3. So 1, 2, 3, 4, and 5. So it's 5-membered ring. Always make sure that your ring sizes don't change, or you're adding carbons or removing carbons when you do this. Okay, so that finishes our aldol reaction, introduction to aldol reaction today. Let's tune in soon for the next one, which will be cross condensations.